In this lecture, we're going to look at electronegativity and bond types. We've done some of this already. We've talked about chemical bonds in Unit 4. We're going to get a little deeper discussion of those today. We've looked at electronegativity. We've defined that, and we looked at the periodic trend for electronegativity in Unit 3. We're going to bring that back into the mix. We're going to look at what I consider to be a spectrum of bonding, a range of covalent bonds where you have completely equal sharing of electrons all the way up to ionic bonds where you have a transfer of electrons from one thing to another. We're also then going to look at bond length in covalent compounds, and then we're going to look at bond energy, how much energy is involved in the formation and the breaking of chemical bonds. Let's define a chemical bond. A chemical bond is going to be the balanced electrical forces of attraction and repulsion between atoms. This attraction and repulsion is going to be between the electrons and the protons. The electrons of one atom are going to be attracted to the protons of another atom. At the same time, the electrons in one atom are going to be repelled by the electrons in another atom. So we have a delicate balance here between the attractions and repulsions. A chemical bond is going to form when the attractions outweigh or are greater than the repulsions between the electrons. This diagram gives us a pretty good representation of what's happening at the atomic level with the energy and the repulsions that are taking place. This y-axis represents the amount of energy associated with the attractions between the atoms. In this case, the negative part down here, below zero, would represent strong attractions. The positive part up here would represent strong repulsions. The x-axis is representing the distance between the atoms. And here you see internuclear distance. So we're going to start off on the right-hand side of the graph here. And notice that these two atoms are very far apart. In a sense, there's very little interaction between them because of their distance. And we can see that based on the fact that our graph is measuring close to zero for our energy. As those atoms get closer together, as we move from right to left, we'll notice that they're getting closer. So here they're represented as being closer. And we also have the energy starting to drop. We've got the attraction between the protons of one atom and the electrons of another atom starting to take place and bond formation beginning to occur. That's why we get the corresponding drop in energy. Whenever we form a bond, our energy is going to get lower. Eventually, we reach a certain point where our bond essentially has formed. Notice here that the two atoms, their electron clouds have overlapped, and now the bond can form. At this point, we've got the lowest amount of energy. They also are at what we would consider to be the ideal distance. If you notice on this graph, if we get these atoms even closer, so notice here they're squished a little bit closer together. That means their electron clouds are forced to overlap even more so, that our energy has started to rise again. And that's because the electrons are getting too close to each other. The protons are getting too close to each other. And what's happening is our repulsions are building up and building up. The closer they get, the higher that repulsion is going to get. And actually it's going to want to push those atoms further apart. That's why this area right here is representing the ideal distance. That distance of 74, what we call picometers, is the ideal distance between these two atoms. It also represents that we have lowered our energy by 436 kilojoules. That's a pretty significant amount. So we have, in this case, formed our bond, which gives us a lower energy state and allows the electron clouds to overlap, and in this case, for the electrons to be shared between the two atoms. Now we've mentioned the attraction between the electrons of one atom and the protons in another atom. The attraction that an atom has for another atom's electrons in a chemical bond is called electronegativity. If you need, go back to Unit 3 and review this. But that measure is essentially a ranking system. Now, in this table here, you'll see that we've got just the S and P elements represented. We're not going to worry too much about the transition metals, although we could look up their values. but this gives us a pretty good idea of what the trends are with how the electronegativities change on the periodic table. You'll notice that in the lower left of the table, we have these low values because the atoms are large, they're not attracting the electrons very well, and they're also atoms that would rather give up electrons and form positive ions. On the upper right, this is where we have our highest values. Those fluorine and oxygen have the highest values on the periodic table. This is because they are small. Because they're small, electrons from other atoms can get close to them and the attraction be very strong. Notice that we don't have any values here for helium, neon, and argon. The reason for this is because electronegativity is measured based on how the atoms act in compounds. That means that an atom would actually have to form a chemical bond before it could go into the ranking system. Helium, neon, and argon have never had any compounds formed from them, so we can't really measure what their electronegativity values are. Krypton and xenon have had some compounds formed, so we can include them in our ranking system. We're not going to usually look at those though, because the compounds with xenon and krypton are very rare and unstable. We can use electronegativity differences to help us identify what kind of a chemical bond we have. What we look at is the difference between the two atoms that are bonded together and what their electronegativity difference is going to be. If the difference in electronegativity is 0, or the electronegativities are equal, we are going to essentially have a nonpolar covalent bond. We'll talk more about what's required for this later. But if the electronegativity difference is extremely low, or extremely small, we can essentially say that they're nonpolar. As electronegativity differences increase, the sharing between electrons becomes unequal. This is because the electronegativity, being a measure of how well they attract electrons, means that if there is a difference in electronegativity, one atom is going to be attracting the electrons more strongly than the other. That means that if there is sharing occurring, the atom that has the higher electronegativity is going to be attracting the electrons more strongly, and they will spend more time around that atom. If the electronegativity difference gets great enough, sharing becomes so unequal that we essentially have a transfer of electrons from one atom to another, and this is what we would call an ionic bond. Notice on this little table or diagram that I have, we've got electronegativity differences represented, and we have some examples of compounds, but nowhere on this do we have a definitive division between polar, covalent, covalent, and ionic compounds. That's because electronegativity is just one factor that we are going to take into consideration when looking at what type of bond we have. Yes, it's pretty safe to say that over here cesium fluoride is going to be ionic because of the very large difference in electronegativity. It also is going to be hinted at by the fact that cesium is a metal and fluorine is a nonmetal, and we've learned that ionic compounds occur between metals and nonmetals. We've also seen down here that if we have an extremely low electronegativity difference, we're pretty sure it's going to be a covalent bond, and what we're doing is just trying to distinguish whether that bond is going to be polar or not, meaning is there going to be any inequality to the attraction between the atoms for the electrons. It's this area here where we get into a gray area. There are compounds that have higher electronegativity differences yet are covalent, and there are some compounds that would have lower electronegativity differences that are ionic. What we have to do is look at other factors. Primarily, if you have a nonmetal reacting with a nonmetal, it's going to form a covalent compound. If you have a metal reacting with a nonmetal, it's pretty good chance that you are going to have an ionic bond. There is no distinction between where ionic bonding and electronegativity differences start and where they end. There's no division between where polar and nonpolar covalent bonds begin and end. It's more of a spectrum. We know what orange looks like and we know what yellow looks like, but where does yellow stop and where does orange begin? Since there's no set division, there's a little bit of a gray area in the sense that we have to look at other factors besides just electronegativity. Now let's talk about covalent bonds. In this case, we're going to talk about nonpolar covalent bonds where the attraction between the electrons is going to be equal. To have a true covalent bond, you must have two atoms bonded together where the attraction is going to be exactly equal. And technically, the only way that this can happen is if you have two atoms that are the same type of atom bonding. Oxygen, hydrogen, fluorine, all of the diatomic molecules that we have, these would be considered purely covalent bonds between the atoms. What this also means is that when that bond is formed, the electron cloud is equally distributed. You'll see here that we have an equal distribution of the electron cloud around these 2 points. The two positive signs represent the nucleus. The chemical bond then would be the area here where you get the highest density of electrons. That represents where the electrons are being shared. Although this entire cloud is where the electrons may be, the higher area probability is where we could consider the bond to be. But the thing is, since it is equal sharing on both parts of the atoms, the distribution of the electron cloud around them is equal. An example of something that's going to be really close to being a pure covalent bond is carbon with an electronegativity of 2.5 and selenium with electronegativity of 2.5. Since they are not exactly the same element, there is going to have to be some imbalance in the attraction between the electrons. Even though they both have electronegativity values the same, there's going to be the very slightest variation, although we could probably consider that to be a nonpolar covalent bond. Polar covalent bonds are going to be caused by an unequal attraction for the electrons. That means that one of the atoms is going to have a higher electronegativity than the other atom. So any difference in electronegativity is going to cause some polarity to occur within the bond. What that means then is our electron cloud is going to be unequally distributed, where we're going to have a lower density of electrons around the atom that has lower electronegativity and a higher density around the atom that has a higher electronegativity. In this case, the bond between hydrogen and chlorine would have a lower density or lower probability of electrons around the hydrogen and a higher probability around the chlorine because of the fact that the chlorine has a higher electronegativity. For polar covalent bonds, we have a very wide range of electronegativity differences we can have. We can have an electronegativity difference of 0.3, and that would be a bond between hydrogen and carbon. We could go up as high as and have a polar covalent bond with electronegativity difference of 1.8 when we have hydrogen bonded to fluorine. An ionic bond then is just going to the other extreme, opposite of what the nonpolar covalent bonds are. It's caused by transfer of electrons, and one atom is going to have to be significantly higher in electronegativity than the other. The significantly larger electronegativity atom is going to attract the electrons from the lower electronegative atom. In this case, we have sodium giving electrons up to the chlorines. When that happens, we form the ions of sodium ions and chloride ions. Now in this diagram, we can see that sodium's atom size has significantly decreased and chlorine's atom size has significantly increased. That occurs because of the transfer of the electron. We now have the sodium cation, positively charged ion, and we have the negative anion of the chlorides. All of those now are going to be attracted to each other because of the opposite charges. Bond length and bond energy are two properties of bonds that we're going to look at a little bit closer later in this unit, but I want to introduce them now. Bond length is pretty simple. It's simply the distance between the two nuclei of the atoms that are involved in the bond. So if you simply measure the distance between the nucleus of one hydrogen atom and the other hydrogen atom in an H2 molecule, you'll see in this diagram here, we would get 74 picometers. If we measure the distance between the two iodine nuclei, so we've got iodine, a nucleus here and a nucleus there, the distance between those of 266, that would be the bond length in the I2 molecule. Bond energy is simply the amount of energy that's released when a chemical bond is formed. Here we see that we've got 4 hydrogens. Those are all going to be bonded to nitrogen, and the 2 nitrogens are going to be bonded to each other. When this molecule forms and these atoms form these bonds, you'll see here that we get energy represented being released by these arrows pointing outwards. Now, the negative 389 value is the amount of energy that's being released by the formation of the hydrogen and nitrogen bond. You'll notice since we have 4 hydrogens being bonded to those nitrogens, we have 4 different values of the 389 to represent each of those bonds that are formed. The negative 163 represents the energy released when the 2 nitrogens bond to each other. All of those together, added together, would be the amount of energy released when that compound into H4 molecule is formed when those atoms bond to each other.